Good morning. Today I am going to tell you something about electric field intensity and the expressions for electric field intensity due to different charged objects. Now, let us see the definition for electric field intensity. Electric field intensity or intensity of electric field at any point is defined as the force experienced by a unit positive charge placed at that point in the electric field. Suppose if this is this entire board is considered to be a region where there exists electric field. So, if you want to find out electric field intensity at any point, you just place a unit positive charge at that point. Then the force experienced by unit positive charge at that point is nothing but it is electric field intensity at that point. So, I am telling you the definition of electric field intensity again. Electric field intensity at any point in the electric field is defined as the force experienced by a unit positive charge placed at that point. So, whenever you are learning the definitions, you should never by heart the definitions. You have to imagine an electric field right in front of you. Suppose if I place a unit positive charge, that positive charge definitely moves in the electric field with some acceleration. If the charge is moving with acceleration, that means it is experiencing some force. Now, I am going to define electric field intensity at the point here. So, electric field intensity at any point is defined as the force experienced by a unit positive charge placed at that point in the electric field. So, as force is a vector, electric field intensity is a vector, right. So, here suppose I told you already, uniform electric field is represented by straight parallel equally spaced lines. So, here if you place a charge q in this uniform electric field, it experiences a force F given by F is equal to Q into E. From this expression, F is equal to Q into E. Force on a positive charge is in the field direction. This is very important. Positive charge experiences a force in the field direction, because if this is the electric field is force experienced by a unit positive charge. Look here, suppose this is a positive charge. This is the point where we want to find out electric field intensity. At the point where we want to find out electric field intensity, we have to imagine a unit positive charge. So, force experienced by this unit positive charge placed at the point P is called electric field intensity at that point. So, this charge repels this. So, electric field intensity due to a positive charge is away from it. Due to a positive charge is away from it. Suppose if this is a negative charge, we want to find out electric field intensity direction at this point. Still we need to imagine a unit positive charge. On this unit positive charge, this negative charge exerts attraction in this direction. So, electric field intensity at any point due to a negative charge is away. So, we can say electric field intensity is a vector from positive to negative charge. Electric field intensity is a vector from positive to negative. Suppose if I write this is the direction of the electric field, this is positive and this side will be negative. if we place a positive charge in the electric field, this positive charge repels and this negative charge attracts. So, direction of force on a positive charge in the field is in the field direction. Similarly, if you place a negative charge experiences a force in a direction opposite to the field. So, on a negative charge, force is in a direction opposite to the electric field intensity. This concept is very important. I am telling you once again, electric field intensity at any point in an electric field is defined as the force experienced by a unit positive charge placed at that point. Electric field intensity is a vector. Due to a positive charge, it is away from it. Due to a negative charge, it is towards. So, electric field intensity direction is from positive to negative. That is the third point. And force on a charge Q placed in a field of intensity E is F is equal to Q E. On a positive charge, force is in the field direction. On a negative charge, force is opposite to the field direction. So, here now electric field intensity is defined as force experienced by a unit positive charge. So, electric field intensity is a vector. It is directed from positive to negative. Now, let us try to write units and dimensional formula for electric field intensity. So, for E, SI unit. For force, it is Newton. For charge, SI unit is Coulomb. So, it is Newton per Coulomb. Later, we also say it is the potential gradient. Hence, another unit for electric field intensity is nothing but volt per meter. Both are same, Newton per Coulomb or volt per meter. So, SI unit, that is. From this unit or from this expression, you can directly write the dimensional formula for E. For force, mLT to the power of minus 2. For charge, AT implies dimensional formula for E is mL, this goes up, T to the power of minus 3, A to the power of minus 1. So, for E, SI unit is Newton per Coulomb or volt per meter. For E, dimensional formula is mL T power minus 3, A to the power of minus 1. Right? Now, force on a charge Q placed in a field of intensity E is QE. So, acceleration of the charge is QE by M. See, if you just have the concept, that concept in your mind, you can do magic with the problems, because from this concept, it is linked with the kinematics. V is U plus AT, S is UT plus half AT square, V square minus U square is 2AS, Sn is U plus A by 2 into 2n minus 1, where we will be using A as QE by M. So, this concept is linked with kinematics and given in JEE main question papers. So, acceleration of a charge Q moving in a uniform field of intensity E is A is equal to QE by M, right. So, this is the acceleration. And force on a positive charge is in the field direction, force on a negative charge is opposite to the field direction. So, that concept is so important. I will give you an important example for this concept. Look here. See, let us go back to the case of a simple pendulum. Okay, in case of a simple pendulum executing simple harmonic motion, how does it execute simple harmonic motion? We just consider a simple pendulum freely suspended. It is pulled aside through a small angle theta and released. Then it executes simple harmonic motion. In case of any simple harmonic oscillator, time period of oscillation is 2 pi square root of y by a. For example, y is the displacement, a is the acceleration towards the mean position. When theta is small, these two are like this. Y is in this direction, acceleration is almost opposite to that. So, that is why in the derivation of time period of oscillation of a simple pendulum, we assume that amplitude of oscillation is small. Look here. So, 2 pi square root of y by a. If it is just under the gravitational field, mg will be in this direction. See here, this is theta. So, its component along this direction is mg cos theta, and the component of weight along this direction, it becomes mg sin theta. So, restoring acceleration a is equal to g sin theta at a displacement y. So, here sin theta is equal to opposite side, that is y by hypotenuse is length of the pendulum. Substituting this here, acceleration will be equal to g into y by L. So, just substitute over there. Time period of oscillation is 2 pi square root of y by a is g y by L. So, T is equal to 2 pi square root of L by g. That is the expression for time period of oscillation of a simple pendulum oscillating in the gravitational field alone. Now, we are going to consider time period of oscillation of a simple pendulum oscillating in the composite field of gravitation and electric field. So, follow me very carefully. This is a simple pendulum with a charged bob, with a bob of charge q and mass of the bob is m, length of the pendulum is L here. It is pulled aside through a small angle theta and released. We want to find out the time period of oscillation. We know time period of oscillation is 2 pi square root of y by a, where y is this displacement, a is acceleration along this direction. Now, here it is in an electric field acting vertically in the downward direction. So, there are two forces acting on the bob here. One is mg and the other one is force due to the electric field, that is QE, force acting in this direction. So, the component of this force along this direction becomes mg plus QE into cos theta. It will be along this direction, that is balanced by tension in the string. Here one model is, it is pulled aside through an angle theta. At that position, what is the tension in the string? That is mg plus QE into cos theta. What is the restoring force acting on it? That is mg plus QE into sin theta. What is the restoring acceleration or acceleration towards the mean position? That is mg plus QE sin theta by m, or we can as well write it as g plus QE by M into sin theta. G plus QE by M into sin theta. But sin theta from this triangle OAB, sin theta is equal to opposite side by hypotenuse, that is y by L. Substituting this in the expression for acceleration, acceleration is G plus QE by M into sin theta is y by L. Take this as equation 3, substitute that here, you get the time period of oscillation as 2 pi square root of y by A is G plus QE by M y by L. So, y and y gets cancelled. Time period of oscillation of a simple pendulum with a charged bob oscillating in a uniform electric field acting in the vertically downward direction is given by 2 pi square root of L by G plus QE by M, right. So, this is the proof for that. Okay. So, I am repeating, this is the expression for time period of oscillation of a simple pendulum with a charged bob oscillating in a uniform electric field acting in the vertically downward direction. If there is no electric field, it is simply 2 pi root L by G. In presence of electric field, denominator is increased, meaning time period of oscillation is decreased. So, this is very important. You have to learn the concept and have to have the grip over the concept. Then in the exam, competitive examinations, definitely you don't have find time to solve all these things. I will tell you a trick here. Okay. Now, look here. This is a simple pendulum oscillating just under the influence of gravity. It is 2 pi square root of L by G. Now, we have a simple pendulum with a positively charged bob oscillating in an electric field applied in the downward direction. So, this is T dash is equal to 2 pi square root of L by, in this direction G is there, in this direction QE by M. Acceleration due to that electric field is there, it becomes 2 pi square root of L by G plus QE by M. How simple is this? So, actually for this, if you just look at that, that's what we have derived after doing all these things. Just from common sense, you can say G and QE by M are in the same direction, T dash is 2 pi root L by G plus QE by M and T dash is less than T here. Now, let us see the third case. Okay. So, the third case is, look here, you have to answer me properly. Okay. This is a simple pendulum with a charged bob. So, G acts in the downward direction. It is oscillating in a uniform electric field acting in the upward direction. So, here acceleration due to that will be QE by M up. So, here T double dash is equal to 2 pi square root of L by G, as this is in the opposite direction, minus QE by M. So, very obviously T double dash is greater than T. Okay. Suppose if you are asked to arrange them in increasing order, T double dash greater than T dash greater than T. That is the increasing order of time periods of oscillation. Okay. Now, you have to answer me. I am going to ask you another question. Look here. See, this is a simple pendulum oscillating in under the influence of gravity. This is 2 pi root L by G. This is a simple pendulum with a charged bob given a negative charge and it is oscillating in an electric field applied in the vertically downward direction. Can you tell me the expression for time period of oscillation in this case? Yes or no? Look here. So, let us, G is in this direction, negative charge experiences a force opposite to the field direction. Force is opposite, so acceleration is also opposite. So, T dash is equal to 2 pi square root of L by G minus QE by M in this case. Now, if you go to another case where electric field is applied in the upward direction, see, G is downwards, force on a negative charge due to the electric field is downwards, hence acceleration due to electric field is also downwards, then T double dash is equal to 2 pi square root of L by G plus QE by M. So, you have to be very careful what is the nature of the charge given to the sphere and also what is the direction of electric field applied. Is it okay? Now, I am going to tell you a question that is given in previous examination, previous exams. See here, as the time period of oscillation of a freely suspended simple pendulum is T. So, time period of oscillation of a freely suspended pendulum is T. Initially, it is not given any charge, so its time period is T, or even if it has a charge, no electric field is applied, so no electric force is there, simply it oscillates under the influence of gravitational field. So, time period of oscillation T is equal to 2 pi square root of L by G. In the next instance, here in case of same simple pendulum with a charged bob, similar charge is placed at the point of suspension. Then what is the new time period? So, you have to find out the new time period. You just guess and tell me the answer. The options given are T greater than T dash, T less than T dash, T equal to T dash and no option, none of the above, because it depends on the magnitudes of the charges given or something like that, the fourth option is given. So, here it is a very interesting question. See, actually to find the time period of oscillation, we are following this method, isn't it? It is pulled aside through a small angle theta. It is pulled aside through a small angle theta. Then at that position, mg will be in this direction. Force of repulsion will be in the electrostatic force of repulsion will be in this direction. The component of mg along this direction is mg cos theta. So, the tension in the string at that position is mg cos theta plus F. Now, look here very carefully. What is the restoring force? The component of this mg along this direction is mg sin theta. Component of this electrostatic force along this direction is 0, because this is radial and this is tangential. Angle between this radial vector and tangential vector is 90. Component of F along this tangential vector is 0. Hence, electric force does not contribute anything to the restoring force. So, there is no influence of a charge placing at the point of support. So, the correct answer is T dash is equal to T. It is independent of the nature and magnitude of the charge placed at the point of support. That question is given twice in previous examinations, once just like this theory, and in another case values are given, you are asked to calculate the time period of oscillation. Even though Q1, Q2 are given, that entire data becomes redundant, because even in this case the formula for time period of oscillation is 2 pi square root of L by G. So, even if you place a charge at the point of suspension, there is no change in the time period of oscillation, right? I think I am clear. Okay, I'll stop here for today. Thank you and bye-bye.